Hello, everyone. Welcome back to our course on abstract algebra. Before we move on to some new topic, I actually wanted to do what we said abstract algebra is supposed to do. It's supposed to abstract algebra. And what we just did in the previous video was prove a big theorem. It was Lagrange's theorem. And then I want to use the general theorem about groups, to prove two other very big theorems, to see that Lagrange's theorem is really a big theorem because it retrieves two of the main theorems, classical theorems from number theory, Fermat's theorem and Euler's theorem. So let me first review what Lagrange's theorem says. Remember, we just proved Lagrange's theorem. Lagrange's theorem says that if you have a finite group G and of order G, the size of G, and H is a subgroup of G, then the order of H divides the order of the group. And this has consequences. So let's see some consequences. The very first one we're going to prove is, as I said, a classical theorem of Fermat, which is called, usually referred to as Fermat's little theorem. And Fermat's little theorem says the following: let P be a prime number, let P be greater or equal to 2 be a prime number, and let A be an integer that is relatively prime to P. There's relatively prime to P, so we have that the GCD of A and P is just 1. Then P divides A to the P minus 1 minus 1. Or in terms of congruences, since we do know congruences, this says that A to the P minus 1 is congruent to 1 modulo P. More generally, if B is any integer, then P divides B to the P minus B, or in other words, B to the P is congruent to B modulo P. So what does this say? This says that, for example, if I take, let's say, P is 5, then things like 2 to the, so P minus 1 would be 4. So this says that 2 to the 4 minus 1 has to be divisible by 5. And this is 16 minus 1, which is 15, which is divisible by 5. This is 3 times 5. What about something like 3 to the 4 minus 1? This is also divisible by 5. 3 to the 4 is 81 minus 1. That is 80. And that is a multiple of 5. That is, 16 times 5. Yes. So those are multiples of 5. Let's take, for example, P equals 7. Then how much is 3 to the 6 minus 1? Is that a multiple of 7? This is 729 minus 1, which is 728. And it turns out 728 is 104 times 7. So it is divisible by 7. So all of these work. The more general form is to say that, for example, well, yes, if I multiply, let's go back to 5. If I take any number and raise it now to the 5th power, then that 2 to the 5 minus 2 will be also divisible by 5. And well, that we know that without, this is 2 times 2 to the 4 minus 1. So this will be 2 times what we already knew was a multiple of 5. So this is a multiple of 5. So this is 6 times 5. But this is more general because it applies to any number. But of course, if the number is divisible by 5 to begin with, the first form was for numbers that are relatively prime to p, but here I don't need the relatively primeness. And of course, this is going to be divisible by 5. This is 5 times 5 to the 4 minus 1, which is a multiple of 5 also, because the 5 is already right there. So all of these hold. So how do we prove Fermat's little theorem? Let me first tell you how one proves Fermat's little theorem in number theory without using abstract algebra. So this is Fermat's little theorem. By the way, we call it the Fermat's little theorem because there is another one that is called Fermat's last theorem, which is a lot more difficult and it took hundreds of years to find a solution of. So Fermat's little theorem without abstract algebra. So how do I prove Fermat's little theorem without abstract algebra? So let A be an integer relatively prime to p. And then what I'm going to do is the following. I'm going to consider the numbers 1, 2, 3, up to p minus 1. And I'm going to do a map. I'm going to multiply them by a. I'm going to do a times 1, a times 2, up to a times p minus 1. Okay, so this is just times a. And now notice that any of those numbers, a times I, if those were congruent modulo p, so if there was a coincidence on this side, then what would happen is that, well, since a is relatively prime to p, a has an inverse modulo p, and I can multiply both sides by a inverse and get that I is congruent to j modulo p. But if I and j are in the set from 1 to p minus 1, that means that if they are in this set, there is nothing that is congruent to each other between 1 and p minus 1 because p is prime, and j minus I will not be divisible by p unless they are exactly the same. So then I is equal to j. What that means is that then the numbers 1, 2, 3 up to p minus 1 and the numbers a times 1, a times 2 up to a times p minus 1 are the same modulo p. And now we can do the following. I can multiply 1 times 2 times 3 up to p minus 1, or I can multiply them in the different order, which was the multiples, all of these multiplied by a. So since those two sets are the same that I just proved, I can also do a and a times 2 and a times 3 and all the way times a times p minus 1. And those two things have to be the same modulo p because I just proved that those two sets of numbers are exactly the same modulo p. But now on the right-hand side, I can take all these powers of a out of there, and you see that there is 1, 2, 3. There is p minus 1 factors in here. So this is a to the p minus 1 times 1 times 2 times 3 times p minus 1. That's what I keep left over after I take all those powers of a out. But now if I call these n and I call these n, it turns out then that what I get is that n is congruent to a to the p minus 1 times n modulo p. And now can I divide by n? Yes, because p does not divide 1 times 2 times p minus 1 because p is prime. That implies that p does not divide n, and that implies that there is an n inverse modulo p. So if I multiply by n inverse, what I get is that 1 is congruent to a to the p minus 1 modulo p, which is what I wanted to show to prove at least the first part of Fermat's little theorem. Great. But so I can do all of this, or I can now prove Fermat's little theorem using our abstract algebra methods. So I'm going to now prove Fermat's little theorem using abstract algebra. And in particular, what I'm going to use is Lagrange's theorem. So what I'm going to consider is the group z modulo p z, but not under addition. I'm going to take the multiplicative inverse, those elements that have multiplicative inverses. So what we called u of p, which are those elements in z modulo p z that have multiplicative inverses. And it turns out that because p is prime, we know what this is. This is precisely 1, 2, 3, up to p minus 1 modulo p, everything except 0, because as long as you are relatively prime to p, you do have an inverse. So this group has p minus 1 elements. Great. So we have that the size of this group is precisely p minus 1. And now by Lagrange's theorem, every subgroup has to divide the order of every group of every subgroup divides p minus 1. So now let A be some element, some integer. Let's just say it's an integer. Let A be an integer. Relatively prime to p. And let's suppose that A is congruent to I modulo p, with I is one of those between 1 and p minus 1. Then consider the subgroup generated by A, which we know is it's the subgroup generated by A, which is, we know that is 1a squared up to a to the n minus 1, where the order of A is n. And by Lagrange's theorem, we have that the size of the group has to divide the size of the subgroup has to divide the size of the group. But this is, in this case, n, and in this case, this is p minus 1. So we have that the size of the subgroup generated by A, which is the size, its incongruences is the size of, in terms of congruences, this is the same as the subgroup generated by this element I. This will divide the size of the group UP, which is p minus 1, and this is n. So n divides p minus 1, where n is the order of A. And if we write p minus 1 as n times k, for some k an integer, then what do we have? A to the p minus 1 will be congruent to I to the p minus 1. We just said that A was congruent to I modulo p. And this will be I to the n to the k. N is the order of I and the order of A modulo p, and therefore that is 1 to the k, and that is 1 modulo p. So what we get is that A to the p minus 1 is congruent to 1 modulo p. So in summary, what has happened here is that this is true. Fermat's little theorem is true simply because UP has size p minus 1, and the order of any element, we showed that the order of any element of the group divides the order of the group. And in particular, any element to the order of the group has to be the identity. And that implies that what we have in this case, that A to the p minus 1 has to be 1 modulo p, which is Fermat's little theorem. Now that we know how to do this, we can do something even better, which is Euler's theorem. So Euler's theorem now says the following: let n be bigger than 1, and let A be a number that is relatively prime to n, some integer, an integer number that is relatively prime to n, then A to what we call phi of n is congruent to 1 modulo n, where phi of n is defined as the number of numbers in the interval from 1 up to n that are relatively prime to n. This is called the Euler phi function. And now you can see that we are going to prove this one. It has a proof that is very similar to the proof I gave of Fermat's little theorem using like number theory, but we can prove this one in a very similar way to what we just did for Fermat's little theorem using Lagrange's theorem, because this is saying that the order of an element divides the order of the group for some group. So what is the group that we're talking about in here is, of course, so here's the proof, is consider z modulo nz cross, which is un. This is a group under multiplication, and these are precisely those numbers between 1 and n that have multiplicative inverses, modulo n. But by a theorem, it turns out that these are precisely those numbers between 1 and n that are relatively prime to n. And that's great, because then phi of n, by definition, counts precisely the number of elements in un. And hence, if A is relatively prime to n, then A to the order of the group has to be 1 modulo n by Lagrange's theorem. because a an element to the order of the group, it always has to be 1, just because the size of the subgroup generated by A has to divide the order of the group. The order of the group is phi of n, and if the order of A divides phi of n, then A to the phi of n is also 1, and that proves Euler's theorem. Okay, so next time we will start talking about homomorphisms and isomorphisms of groups.